Okay, let's go ahead and get started. So, expected value, a key with expected value is that it's what's going to happen over the long run, not the outcome of a single event. It's what happens over the long run. And the distinction there would be something like this. If we were to say flip a coin 6 times, we might get all 6 heads. And that would be unusual, but it could certainly happen. Um, and we might think, gosh, on the next flip, it's got to be tails because you had so many heads in a row. Maybe, maybe not. When we're talking about expected value, we're talking about the long run, meaning what would happen if we did 1,000 flips or 5,000 flips? We would expect pretty close to half of them to be heads and half of them to be tails. So keep that in mind when we're looking at expected value. We're talking about the long run, not just a single individual outcome. And we'll see that in some of the examples we do today. I'll make sure to make that distinction for you. I mentioned that expected value is driven by a formula. And in order to build that formula, what we're going to do is we are going to look at different events that happen. And those events are going to have different results. And each one of those results is going to have a probability that goes with it. And it's those results and probability that we're going to use in our formula for expected value. This will make more sense when we actually start using numbers and put them in. But just to sort of get us started down the road, our formula for expected value looks like this. The expected value for some event is the probability of result number one multiplied by whatever result number one is. And then we're going to add that to the probability of the second possible result multiplied by whatever that result is. And we do this all the way down the line till we get to our last probability of our last result multiplied by whatever that last result is. And I realize this might feel very abstract right now. That's okay. We're going to put some numbers in here and that will help make sense of it, I promise. But for right now, it's probability times result, probability times result, probability times result, however many we have, and then we add those together to get the expected value. So that's the formula we're going to use to find the expected value of a bunch of different types of events. Let's take a look at one. So we have this spinner, and let's say you're at a carnival and you're going to play this game, and it has a pointer right there, and you're going to flick that pointer and it's going to spin around and it's going to land in either here in the win $10, down here in the lose $4, or over here in the lose $7. It's going to land in one of those three regions. And we want to know what's the expected value of this spinner. Looking back to the formula for expected value just for a second, what we have there is we need probabilities and results. So let's take a look at what we've got here. We're going to put a table of that together to organize this. We have different results that can happen, and each of those results is going to have a probability that goes with it. So here I can see, looking at my spinner, that the three different results I have are that a player could, and I'm just starting at 12 o'clock and going clockwise, but you could put these in any order. It doesn't really matter. But a player could win $10. A player could lose $7. Oops, I didn't go clockwise, did I? Lose $4 or lose $7. Those are the three things that could happen. Win 10, lose 4, lose 7. Now what we want to do is write down the probabilities that go with each of those individual results. So looking at this spinner, assuming everything is fair, how much of the spinner is taken up by the possibility of winning $10? How much of the spinner is right there? And don't overthink it. Your instinct is correct. How much of the spinner would be win $10? 25%. Very good, Nicole. If we wanted to write that as a fraction, what would it be? If we wanted to write it in sort of our successes over outcomes kind of way as a fraction, what would it be? How much of the spinner? And your 25% is exactly right. But as a fraction, what would we have there? 1/4. Perfect. So the probability of winning $10 is 1/4. 1/4 of the time that you spin this, you would expect to win $10. All right. The next result we see down here is this lose $4. What probability goes with losing $4? What's the probability of that happening? 2/4. Excellent, Nicole. Most of you may have thought right out of the gate 1/2, and that's perfectly fine. I'm going to go ahead and write this as 1/2, but I really like Nicole's 2/4, and you'll see why when we go to evaluate this thing. For right now, I'm going to call it 1/2 because you might look at that and say, well, that's half the spinner, so I'm going to call it 1/2. That's great. I'll show you why Nicole's 2/4 is really good here in just a minute. And then the -7, that's the same as the +10. That's going to be 1/4 of the spinner. So what we have now over here in this box is we have our results and our probabilities. That's everything we need to find the expected value. Remember, the formula for expected value is probability of outcome number 1 multiplied by result number 1 plus probability of outcome number 2 multiplied by result number 2, and so on until we get to the very end. So now let's plug this into our formula and see how the expected value shakes out. So the expected value of this spinner would be, all right, probability number 1 would be 1/4, and result number 1 is going to be the winning $10. One way that I really like to think of this when I write down the expected value part is 1/4 of the time the player is going to win $10. It's the probability times the result. How often is this result going to happen? 1/4 of the time they're going to win $10. And then we do this right down the line. Plus probability number 2, which is 1/2, times result number 2, which is lose $4. And then probability number 3, which is 1/4, times result number 3, which is lose $7. And now we've set it up. Just to sort of refresh what we've got going on here for a second, we've got 1/4 of the time they win 10, 1/2 of the time they lose 4, 1/4 of the time they lose 7. That's what we've set up in our expected value equation. When we simplify this, we'll have our expected value. In order to do this, we need to remember how to multiply fractions. Let's see, this is a fraction times a whole number. More comfortable if I rewrite this as a fraction. Instead of 10, we'll make it 10 over 1. Instead of 4, we'll make it 4 over 1 and 7 over 1. And now we'll go ahead and do our multiplying. And when we do our multiplying, we'll have expected value is, all right, multiply numerators, 1 times 10. Multiply denominators, 4 times 1. Multiply numerators. The negative is very important. So when we have 1 times -4, make sure you keep that negative. 1 times -4 will be -4 over 2 times 1. And 1 times -7 will be -7 over 4 times 1. Now we need to add these fractions. And we saw this a couple days ago. When we want to add fractions, we're going to need a common denominator. And right now, we don't have that. Our denominators are 4, 2, and 4. In order to add these fractions, we need the denominators to be the same. What's a good choice for a common denominator here? What will 2 and 4 both go into? Excellent, Genesis. 4. So I'm going to rewrite all of these fractions with 4 as my denominator. You could use 8 if you want to, but 4 is simpler. So our expected value will be, all right, I'm going to use 4 as my denominator, so this one's okay. Here, I'm going to change the denominator to 4. I've multiplied the denominator by 2, so I need to multiply the numerator by 2. And then this one already has a 4, so I'm okay. Now I've got common denominators. So now I can go ahead and add these together. When I do that, the denominator is going to stay the same. The numerators, we just need to add those. 10 minus 8 minus 7. So let's see, 10 minus 8 minus 7 is negative 5. I end up with negative 5 over 4. Oh, how do we get to negative 8? Great question, Escadar. We did this. In finding, when we wanted to change this 2 to a 4 in the denominator, we have to multiply by 2. And if we multiplied the denominator by 2, in order to keep the fraction having the same value, we also have to multiply the numerator by 2. So the negative 4 got multiplied by 2 to become negative 8. What we're saying there is this, that negative 4 over 2 has the same value as negative 8 over 4. If we multiply the denominator by 2, we also have to multiply the numerator by 2 so that the fraction keeps the same value. All right. We've simplified this. We have negative 5 over 4. What we're going to do with expected value questions, though, is we are always going to write those in the form of a decimal. So we're going to take one more step and do that negative 5 divided by 4 and end up with negative 1.25. So our expected value for this particular spinner is negative 1.25. An important thing to note here is this. Remember, expected value is what happens over the long run. In one particular spin, a player can't lose $1.25. The only thing that could happen in one spin is they would either win 10, lose 4, or lose 7. That's it. Those are the only possibilities. There's no way that in one spin they could lose $1.25. But over the long run, over the long term, they're going to lose $1.25 per spin. And that's what the expected value tells us. If you're the carnival, what this tells you is that over the long run, over the course of the entire day with lots and lots of people playing this game lots and lots of times, you can expect to profit $1.25 per spin. I want to go back and address what Nicole mentioned when she did probability earlier. But before I do that, I want to see if you have any questions on what we did there to find that negative $1.25 per spin. So let me know if you have any questions about anything we just did there in that computation. And then we'll go look at what Nicole did with the negative 2/4. Okay, where at? Where did the confusion happen? Yeah, we're not going to leave expected values as fractions. We're going to go ahead and convert those to a decimal because really expected value is primarily going to be about dollars and cents. So we're going to convert it to a decimal. And if you're not exactly sure where you got confused, Madison, I can tell you we're going to do this formula over and over and over and over and over again. This formula is essentially what we're doing in class today. And we're going to see it in several different scenarios. Essentially, what we did was this, walking back through it. We found our probabilities and results, and then we wrote them out using the formula for expected value. Probability times result, probability times result, probability times result. Now it's just a matter of simplifying this. You got to lean back into your Math 122 a little bit and remember how to work with fractions. And a little practice with fractions is never a bad thing. We multiplied these fractions by multiplying numerators, multiplying denominators. That's what got us here. In order to add fractions, we have to have a common denominator. We can't add when our denominators are 4, 2, and 4. They all need to have the same denominator. And so in order to get a common denominator, we multiplied by 2 on the bottom, so we multiply by 2 on the top. Now that we have a common denominator, we can add those fractions, which is just adding the numerators and keeping the denominator the same. And then we add those together and end up with negative 5/4. And negative 5 over 4 really just means negative 5 divided by 4. And when we divide, we end up with negative 1.25. Very briefly, I want to take a look at Nicole's 2/4 there for probability. So bear with me here for just a second. Okay. If we get rid of all that, and then instead of using 1/2, if we decide to write this probability as 2/4, and you might be thinking, why would I even think to use 2/4? Here's why. We know eventually we want these probabilities to have the same denominator. So as soon as I put that 1/4 on there, I'm thinking, I'm going to use 2/4. It's the same as 1/2, and I already have that common denominator that I need. When I go to write my formula now, I get 1/4 times plus 10, 2/4 times minus 4, and 1/4 times negative 7. And now when I multiply, I get 10/4 plus, let's see, 2 times negative 4, that's negative 8/4 plus negative 7/4. We end up with the same answer. We better. But the key here is basically I'm going to have a common denominator. I can take care of the common denominator over here when I'm working on the problem, or I can take care of the common denominator here when I write down my probabilities. This is exactly right, Lorraine. It saves us a step that we're going to have to do eventually. So we can go ahead and write the probabilities with a common denominator so we don't have to fool with it when we're over here working with all of these other numbers. We still end up with the same negative $1.25 as expected value. So I really like Nicole's 2/4 for probability. It's not wrong if you do it as 1/2. You'll just have to get a common denominator later, which is probably okay. Any other questions about this before I have you try one? Awesome. Here goes. Find the expected value of that spinner. And I'll set up a poll for this one, and we'll see how it goes. This is your first time through the formula for expected value. Be patient, be careful, find your results and your probabilities. Make that little table over here in the corner before you go into the formula for expected value. That's my advice. All right, I'll let you try it. So as you work through this one, we're finding our results and our probabilities. We're plugging those into the formula for expected value and then simplifying to get the expected value. You may want to use 2/4 as the probability of that lose $9 down there at the bottom instead of 1/2, because that would save you a step when you're working through the problem later on. We'll go another 30 seconds on this and then talk through it together. If you need more time, let me know. Okay, you got it. Oh yeah, if you get an answer that's nowhere on there, pick the one that's closest to yours. That way I'll know that you've had enough time to solve it. Okay, 30 seconds from now, we'll go ahead and talk about it. And if you want more time, you can tell me that too. It's okay. All right, let's take a look and see where we are. Okay, not unanimous, strong agreement. That's a good thing. That's kind of typically where we land. We're going to work through this together. You let me know if you aren't sure where something came from or if you have any questions. Because this is an expected value question, the first thing we know we want are our results and the probabilities that go with those results. So as I look at my spinner here, I can see that, let's see, losing $3 could happen, and that's 1/4 of the spinner, so I would expect that to happen 1/4 of the time. Losing $9 could happen, and that's half of the spinner, so I would expect that to happen 1/2 of the time. But I know I want these probabilities to have the same denominator, so instead of 1/2, I'm going to go ahead and call that 2/4 right here. Essentially what we've done is we've created an equivalent fraction. We multiplied the denominator by 2, we multiplied the numerator by 2, and that's why 2/4 is the same as 1/2. Finally, I have win $14 that we expect to happen 1/4 of the time. So now I've got all the information I need right there to find the expected value. Expected value here is going to be, let's see, probability times result plus probability times result plus probability times result. I think through it as probability times result, but if you are comfortable, if you're more comfortable with 1/4 of the time, they're going to lose $3. 2/4 of the time, they're going to lose $9. And 1/4 of the time, they're going to win $14. If that helps you make sense of the formula, then that's great. Absolutely go through that in your head. We just need to simplify it now, and our expected value will be, make these into fractions so that we can multiply. 1 times -3, 4 times 1, 2 times -9, 4 times 1, and 1 times 14, 4 times 1. Now we have a common denominator already. That was kind of a nice feature of changing that probability to 2/4. We already have a common denominator, so we can go ahead and add these together. And our denominator is going to stay the same. That's going to stay 4. And when we add those, -3 minus 18. I don't really trust myself to do that. So -3 minus 18 is -21. And then plus 14 is -7. And so I end up with -7 over 4. And when we divide that, we end up with -1.75. And that's our expected value here. It means that a player would expect to lose $1.75 per spin. They can't lose that in one spin because that's not one of the outcomes. But over the long run, a player would expect to lose $1.75 per spin. If you had trouble with that and you don't see where your mistake was, or you're not sure where it went wrong, please don't hesitate to ask. This is the essence of expected value: finding our results and our probabilities and using the formula to calculate what the expected value would be. We are going to look at a whole bunch of different situations coming up next, but at its heart, this is expected value. Okay, let's look at a different one. A roulette wheel. Some of you may be familiar with the roulette wheel, some of you may not. Just to make sure, this problem will go ahead and let us know what's involved there. The wheel contains 38 slots, and they're numbered 1 through 36, and then there's a 0, and then a double 0. The 1 through 36, half of those are red, half of those are black. Both of the zeros are green. The main thing here is there are 38 slots on the roulette wheel. At a certain casino, if you bet $1 on the number 26 and you win, the house pays you $35. Like I said, some of you may be very familiar with roulette, some of you may not. So we're going to work through this one together. What's the expected value of betting on that number 26? Now, one of the things I have to point out to you, the fact that it's number 26 isn't really important here. It would be the same if you bet on the number 17 or the number 4. That doesn't really matter. If you pick any individual number and the ball lands on that number, then you win $35 for every $1 that you bet. So the 26 isn't going to be part of our results or our probability here. That would be the same if it were 11 or 19 or any other number. That part doesn't really matter. It's betting on a single individual number is what results in that $35 win. So here, when we go to set up our results and our probabilities, let's see. So results, there's two things that can happen. They spin the wheel and it lands on my number and I win $35. The other thing that could happen is it doesn't land on my number and I lose. And because I had bet $1, then that's what I would lose. I would lose $1. So those are the two things that could happen here: win 35 or lose 1. Okay. Since we're in the middle of a whole big section on probability, I'm going to ask you about the probabilities here. Keeping in mind that there are 38 slots on the wheel, what's the probability that it actually lands on my number? What would that probability be? And this is a successes over outcomes review. Excellent, Natalie, Nicole, Lorraine, fantastic, very good. That's excellent. I've got 38 slots on the wheel. Only one of them is the number 26. So there's one success out of 38 outcomes. There's two ways to think of the other one. We're going to have 38 outcomes as far as this probability is concerned. Let's see. What would the probability that it doesn't land on my number be? So this probability right here, what's the probability that it doesn't land on my number and I lose? Excellent, Natalie Verlaine, very good. This isn't always easy, so this is terrific. Yeah, and there's two ways to think of that. If there's a 1 out of 38 chance that it does land on my number, then there must be a 37 out of 38 chance that it doesn't. The other way to think of it, well, there's 38 slots on there that are total. One of them is the way that I would win. So the other 37 is how I would lose. So as far as losing is concerned, there are 37 successes out of 38 outcomes. And so that's our probability. And now we have everything we need. We have our results and our probabilities. We can find the expected value. So our expected value here is going to be, let's see, probability times result plus probability times result. And if you're thinking, gosh, 1 out of 38, that's not really a fraction I'm that comfortable working with, keep in mind as you look at these, it's kind of nice. They have the same denominator. So when we go over here, we're already going to have a common denominator. So that's not going to be an issue for us. We'll multiply these together. 1 over 38 times 35 over 1 will give me 35 over 38. And then 37 times negative 1 will be negative 37 over 38. And while these aren't the most comfortable fractions to work with, we already have a common denominator. So that denominator is going to stay. 35 minus 37 will be negative 2. Negative 2 over 38. Since this is an expected value, we'll convert that to a decimal. And I end up with negative 0.05263. And that keeps going. Since this is a question involving money, dollars and cents, we are going to round to the nearest cent, which means we're going to round to the nearest hundredth. And you'll be given instructions about that in the problem. But if it involves money, we're going to round to the nearest hundredth. So we'll find the hundreds place. We'll look one space to the right. That's 4 or lower. So we'll round this down to negative 0.05. What that means is the expected value of betting on a single individual number, betting $1 on a single individual number is losing 5 cents per spin. Doesn't sound like a lot, but if you happen to be a casino and every time everybody bets $1 on a number, over the long run, you're going to make 5 cents on that dollar. You multiply by the number of people playing, by the number of wheels that are spinning, it adds up to be a pretty big number. So essentially, expected value and the long run is kind of how the gambling industry operates, is what's going to happen over the long run. Main thing here is with expected value, we find our results, the probabilities that go with them. We set up the formula for expected value, and then we simplify it to get the expected value for a given event. Any questions on that one before we look at something different? Thanks, Nicole. Okay. Sometimes we might be given percents instead of probabilities. We saw this with our successive events problems on Tuesday. Rick is going to invest money into a stock. There's a 28% chance that he makes $1,000. There's a 58% chance that he loses $300 and a 14% chance that he breaks even. What's the expected value of Rick's investment? First thing I want to mention here is the term breaks even. That means he comes out neither ahead nor behind. He just broke even. He made zero. He lost zero, however you want to phrase that. He didn't make any money. He didn't lose any money. He broke even. So just same place that he started, zero. Once we see expected value in the question, we know we're going to set up our results and our probabilities because that's how we're going to find that expected value. And there are 3 different results here. He could make $1,000. he could lose $300, or he could break even, which is 0. Let me know if you see something that doesn't make sense or you're not sure of it. Now we're looking at probability. Okay, well, the probability that he makes $1,000 is 28%. We'll write that as a decimal. Essentially, what's going to happen here is, just like it was with the successive events on Tuesday, if we're given the probabilities as percents, then we're just going to work with decimals instead of working with fractions. That's okay. And let's see. The probability that he loses 300 is 58%. We'll write that as a decimal. And the probability that he breaks even is 14%. We've got our results and our probabilities, so we can find expected value. Let's see. For the first one, we're going to do probability times result plus. Now the next one, probability times result. And then the last one, probability times result. Let me know if you see something that doesn't make sense. Now we're going to start our multiplying. We'll do 0.28 times 1,000 and get 280. And then let's see, we'll have 0.58 times negative 300 will be negative 174. And then 0.14 times 0 is just going to be 0. Then we add those together, the 280 minus 174, and we get 106. So the expected value here for Rick's investment is that he is going to profit $106. If it were a negative number, that would mean he would expect to lose $106. But since this is positive, we would expect a profit of $106 on this investment. Any questions on anything we did there, working with the percents and the decimals? All right. Here's a little bit of a different situation that has a small twist to it from what we've done so far. Here we're going to look at the expected value of a raffle. And if any of you have ever bought a raffle ticket, this will make perfect sense to you. The key when we look at a raffle is that you don't get the cost of the ticket back. I'll read the situation and I'll talk about that in a little more detail. 500 raffle tickets are sold for $2 each. There's a grand prize of $200 and 2 second prizes of $50. What's the expected value for someone who buys one of these raffle tickets? So as we read through this question, we see expected value, so we go straight to results and probabilities. In the results column, that's where the idea of a raffle becomes really important. Because here's the thing. I buy my raffle ticket and I might win the grand prize. If I win the grand prize of $200, they're going to give me $200, but I don't come out $200 ahead of where I started. And the reason for that is because they don't give me the money I paid for the ticket back on. Oh, Nicole, you may be way ahead of me on this one. Excellent. Very good. Outstanding. You're exactly right. Sure, they're going to hand me $200, but you know what? When I bought that ticket, I paid $2 for it and I don't get that back. So instead of coming out $200 ahead, if I'm the grand prize winner, I'm $198 ahead. That's the key with raffles. Because we had to pay that $2 up front, we don't get that back when we're the winner. They hand us our $200. Correct. We paid the $200 to come out $198 ahead of where we started. That's right. We paid the $2 to come out $198 of where we started. So with that in mind, let's say I win one of these second prizes. what's my result going to be over here? Because they're going to hand me $50, but what's my actual result over here? I didn't really win 50. How much did I win? Very good. Lorraine, Nicole, Carolina, Natalie, perfect. I win 48. That's exactly right. Sometimes with raffles, we forget about the other thing that can happen. So I'll tell you, there's a third thing that can happen here. I could win 198. I could win 48. What's the other thing that could happen here? Very good. Excellent. You're all exactly right. I could lose the $2. I bought a ticket. I got nothing back. I wasn't one of the winners. I had a losing ticket. So I lose $2. Now we need the probabilities that go with each of those. So let's see here. There was a single individual grand prize winner, and there were 500 tickets sold. So the probability of that is 1 out of 500. Let me know if you see something that doesn't make sense or is confusing at all. And then there are 2 of these second prizes. So there's 2 chances to win. So the probability there is 2 out of 500. And then again, it's easy to forget about the losing ticket part. It's also like, what the heck is this probability going to be? Like, okay, so I know there's 500 tickets, so I'm good with 500 outcomes. What we have to think about here is how many of those tickets would be losers? Very good, Lorraine, you nailed it. 497. There's 1 grand prize, there's 2 second prizes. So if I started out with 500 tickets and I take away the grand prize, now there's 499 tickets still out there. If I take away the 2 second prizes, that leaves me with 497 tickets that they aren't going to win anything. They're just going to be losing tickets, 497 of them. The other 497 tickets are going to be losers. So the probability of losing $2 here is 497 out of 500. Now I've got my results and my probabilities. I'm ready to find the expected value. Notice every one of these has the same denominator. So we're not going to have to worry about finding a common denominator. It's already going to be in there for us. So our expected value here is going to be 1 out of 500 is the probability of winning $198. 2 out of 500 is the probability of winning $48. And then 497 out of 500 is the probability of losing $2. Now we've got it set up. We're about ready to finish off our calculation. Are there any questions about how we got to here? Where these results and probabilities came from? And I want to emphasize that the main thing that's different about raffles is we don't win the whole 200 because we had to pay this $2 up front. Okay, let's go ahead and finish this off then. So we'll multiply and have 198 over 500. Multiplying 2 times 48, let's see, that's 96 over 500. And then 497 times negative 2. I'm not going to try to do that. Negative 194 over 500. Kind of a big, ugly number, I'll grant you that. But it's okay. We already have common denominator. So adding these won't be too bad. We know we're going to end up with 500 on the bottom. And let's see, we have negative 994 plus 198 plus 96 is negative 700 over 500. Careful there, Escadar. You make sure that you have the negative with the appropriate number, and just be careful when you add those together. And then finally, negative 700 divided by 500 to get our decimal answer is negative 1.4, which this is dollars and cents, so we might say negative $1.40. Yeah, that's negative 994. Yeah. And that came from 497 times -2. That's where the negative 994 came from. Because just like we did with the others, we convert those to fractions and multiply numerators together, multiply denominators together. Multiply numerators, multiply denominators, multiply numerators, multiply denominators. And so the expected value of buying one ticket is that you would lose $1.40 per ticket. Obviously, with one ticket, you can't. The only possible outcomes from buying one ticket are plus 198, plus 48, and -2. Are there any questions about what we do with that raffle before I let you try a raffle problem? All right, here goes. 100 raffle tickets are sold for $5 each. There's a grand prize of 300 and a grand prize, so there's only one second prize of $75. What's the expected value for someone who buys one of these raffle tickets? So remember, you don't get your $5 back. Find the results, find the probabilities, and then find the expected value for buying a ticket in this raffle. I'll set up a poll and let you try it. Just like before, if you come up with an answer that's not one of the choices, pick the one that's closest to yours so that I know you've had enough time to finish it. And then as we work through it, let me know if you have any questions. And this is just another example of us working with the formula for expected value. We need our results. We need our probabilities. We put them into the formula and then simplify. Just be patient and careful every step of the way. I'm thinking we'll go another 45 seconds. If that's not enough time, you can let me know. Good thing. No problem. No, I definitely want everyone to have a chance to try it. I do think as far as expected value problems go, where you're just finding the expected value, the raffle problems are probably the most challenging. Um, really, just because we have to remember that we don't get our money back. The idea behind an expected value problem is basically the same every time. We're going to do results and probabilities, use our formula to set up an expression to simplify, or something we'll look at later on that's slightly different from that. But still, we're going to find our results and our probabilities and use the formula. That's going to be our approach with expected value problems. Remembering your remembering how to work with fractions back from 122 is pretty important. Um, and that's something that we can review if necessary. Um, but that fractions do come up for us here because our probabilities are generally going to be in the form of fractions. They sometimes are decimals, like we saw in that investment example, but most often we're going to see probabilities written as fractions, and then we're going to work with those fractions. I'm thinking maybe another 30 seconds. If that's not enough time, you let me know. Okay, let's see where we are on this. Okay, strong agreement, but we're spread around all those answers. So let's be patient and careful as we go through this one. If you that you're not sure where it came from, let me know. If you can identify your own mistake, there's a lot of value in that. If you can't, that's okay. You can absolutely ask about whatever it is that might be giving you trouble here. All right, so we read through the question, and 100 raffle tickets are sold for $5 each. There's a grand prize of 300 and a second prize of 75. What's the expected value for someone who buys one of the tickets? As soon as we see the expected value, we're going to have results and probabilities. And our results here, well, let's see. I could be the grand prize winner, which is a $300 prize. So plus 300, but wait a minute. I don't actually come out $300 ahead because I had to pay $5 for a ticket. So even if I'm the grand prize winner and they hand me that $300, I'm not $300 ahead of where I was because I paid $5. That's right, Escadar. I am $295 ahead of where I was before. I could also win a second prize. If I win the second prize, that's a $75 prize, but I still paid $5 for a ticket. So I'm not $75 ahead of where I was before. I am $70 ahead of where I was before. And then we don't want to forget about the fact that maybe I don't win anything at all and I just lose $5. All right, we've got our results. That's everything that could possibly happen. 295 ahead, 70 ahead, or lose 5. Now I need the probabilities that go with those. Let's see, there's a grand prize and there's 100 tickets. So the probability of winning the grand prize is 1 out of 100. There is a second prize. So there's only one second prize out of 100 tickets. So the probability is 1 out of 100. And then finally, well, if there's one of these and one of these, then that means there's 98 tickets out there that are losers. So the probability of losing $5 is 98 out of 100. I've got my results and probabilities. Now I can go find the expected value. So 1/100th is the chances that will come out 295 ahead. 1/100th is the chances I'll come out 70 ahead. And then 98 out of 100 is the probability of losing $5. And now we just need to simplify. If you have questions on how we got to here, it's okay to go ahead and ask those. And then a little bit of fraction review. We're going to rewrite those whole numbers as fractions so that when we go through and multiply, we're going to multiply numerators together, multiply denominators together. And so we'll have, let's see, 1 times 295 is 295. 100 times 1 is 100 on the bottom. 1 times 70 is 70. 100 times 1 is 100 on the bottom. Right, because the 300 is not a part of this at all. Yeah, there's no 300 anywhere. There were 100 raffle tickets, so that's our denominator here. You know, basically that's a probability, which is successes over outcomes, and there's one success and 100 outcomes. So that's where those probabilities come from, is successes over outcomes. And that's great. When you see your own mistake, that means you understand what happened, and that's good. Yeah, so these probabilities don't come from nowhere. They come from successes over outcomes. Remember, the most important thing about probability is successes over outcomes. And if I have one success and 100 outcomes, then the probability is 1 out of 100. All right, finishing this up, 98 times -5. That one I'm not going to do in my head. We'll have to do 98 times -5 is -490. 100 times 1 is 100. And then we'll add those together. We've got 100 as our denominator. And let's see what we've got there. We've got 295 plus 70 minus 490 is -125. And then -125 over 100, we'll divide those and end up with -$1.25. So the expected value of buying one ticket here is to lose $1.25. The -490 came from multiplying these two fractions together. We did 98 times -5 because those were in our numerator. Eskadar, last time, in the last problem we did, this one here, there were 500 tickets sold. In this problem, there were only 100 tickets sold. And so it's successes over outcomes. In this one, there were 500 outcomes. In this one, there were 100 outcomes. So that's why those are different. Good, Karina. That's excellent. Yeah, very good. And Stephanie, did that fix where the 490 came from? Was when we multiplied these two fractions together, our numerator was 98 times -5, and that's where the 490 came from. Okay, keeping in mind that probability is always successes over outcomes. In this one, there's one grand prize, so one success out of 100 outcomes, and there is one second prize, so one success out of 100 outcomes. And so that's where those probabilities came from. To find the probabilities, we're just doing successes over outcomes. Okay, perfect. Perfect. We'll emphasize the probability in the next one we look at. Fair price to pay. A game involves 4 ducks that are on a table. A player wins the amount on the bottom of the duck they choose. So you pick up a duck, turn it over, it has a monetary amount on the bottom, and you win however much is on the bottom of the duck. One duck has $5, one duck has $9, and two of the ducks have $1. What is a fair price to pay to play this game? The key here is that the fair price to pay is the same as the expected value. Fair doesn't mean like what would a reasonable number mean. Fair in this context means the the house, the carnival, whoever's running the game doesn't have any advantage and neither does the player. We expect you to break even over the long run. So when we say fair price, we mean that over the long run, you're going to break even. Nobody's going to have an advantage over anybody else. So if you're asked, what's the fair price to pay? That's the same as the expected value. Because if your expected payout is the same as how much you pay to play the game, then nobody has an advantage. And that's what we're looking at here. All righty. So when we read through it and it says, what is a fair price to pay? To us, that means find the expected value, which means we're going to have results and probabilities. Let's see our results here. I could flip over a duck and get $5. I could get $9, and I could get $1. That's what's going to come to me as a player, 5, 9, or 1. Now I need the probability of each, keeping in mind that there are 4 ducks on the table, so the total number of outcomes is 4. With that in mind, the probability that I'm going to get a $5 duck, well, there's one of those. So since there's one way to get $5 out of 4 possible outcomes, the probability of that is 1 out of 4. Okay, getting a $9 duck. Well, one duck has $9 on it, and there are 4 outcomes. So the probability of getting the $9 duck is 1/4. And then 2 ducks have $1 on them. So the probability of getting a $1 duck, there's 2 successes and 4 outcomes. So that probability is 2 out of 4. And now I have my results and probabilities, so I can find the expected value. The numbers are kind of nice here. The key to this problem is fair price to pay and expected value are the same as each other. So 1/4 times plus 5 plus 1/4 times plus 9 plus 2/4 times plus 1. We're going to convert those whole numbers into fractions so that we can multiply. And then after we multiply, we'll have, let's see, 5/4 plus 9/4 plus 2/4. And that was just multiplying numerators, multiplying denominators. Multiply numerators, multiply denominators, multiply numerators, multiply denominators. Finally, we add those together. 4 is going to be our denominator. 5 and 9 would be 14, and 2 more is 16/4. We divide those and get $4. A fair price to pay to play this game would be $4. If you had to pay $4 when you walked up to play, then you wouldn't make any money, and neither would the carnival or the house or the school or whoever's running this game. If you're a school running this game, now you know you don't want to charge $4 because you won't make any money. You need to charge more than 4, maybe 5, maybe 6, so that you make money every time someone plays. Are there any questions on that before we move on to one more expected value topic for today? All right. This one's about fair games also, but we're going to change it up a little bit. Um, a card is selected from the hearts that are in a standard deck. If the card is the ace, the player wins $84. So what you've got here is you have the hearts on a table and they're all mixed up. And you get to pick one. And if it's the ace, you win $84. In order for this game to be fair, when the player loses, how much must they lose? This is the first question we've seen today that didn't ask us for expected value, but it is an expected value question. And the way we know that is because it said, in order for this game to be fair. For a game to be fair, the house has no advantage and the player has no advantage. So what that means is if this is going to be a fair game, the expected value has to be equal to 0, meaning no advantage to either side. A player's not going to win money, a player's not going to lose money. The expected value has to be 0. Okay. So even though expected value is not in the question, when it says in order for a game to be fair, that tells me something. That tells me the expected value of this game has to be 0, which means, well, it's kind of disguised in there, but this is an expected value question. So we need results and probabilities. So the results here, well, if the player gets the ace, they win $84. So win $84 is one of my results. If they lose, I don't know how much they lose. That's actually what the question is asking for. How much must they lose? We don't know what that is, so we'll call it X. That's how much they lose if they lose. If this feels a little abstract right now, that's okay. All right, well, what's the probabilities then? Well, let's see. There are 13 hearts in the deck, and the ace is the only one they win with. So the probability that they win is 1 out of 13. The probability that they lose then, that's if they pick anything else except for the ace. Well, that's all the other hearts that are in there. That's 12 of them. So the probability they lose is 12 out of 13. And at this point, we have all the information we can gather. We know what the results are. We know what the probabilities are. We're trying to figure this thing out. And here's how we'll do that. We're going to set up our exact same expected value equation. The expected value is going to be 1/13 times plus 84 plus 12/13 times x. And at this point, you might be thinking, okay, but how do I do this? I don't know what x is, and that's fair. The thing is, we don't know what x is, but what we do know is that the expected value has to equal 0. For this to be a fair game, the expected value has to equal 0. So backing up just a quick step here. Our results are win 84 and I don't know. The probabilities are 1/13 and 12/13. That allows us to set up this over here. And since we know in order for a game to be fair, the expected value has to be 0, that allows us to set up this equation. We don't do a ton of algebra in Math 123, but this is a time we are going to do some algebra. We're going to solve that equation for x, and then we'll know how much they have to lose in order to make this a fair game. So let's do a little algebra here. So we're going to have 0 equals, we can go ahead and multiply that. That's 84 over 13 plus 12/13 x. When I'm solving an equation, I'm trying to get x by itself, which means I need the term with x by itself. And so as far as I look at everything on this side, I'm going to peel it from the outside in. I'm going to get rid of that 84/13 first. It's a little ugly, but what we're going to do is subtract 84/13 from both sides. On the right-hand side, those cancel. And what that leaves me with is I've got negative 84/13 on the left, and that equals 12/13 times x on the right. Okay. I'm trying to get rid of 12/13. Anybody remember what I need to do to get rid of 12/13? What do I multiply by to make 12/13 go away? If you don't remember, it's okay, but if you do, that's excellent. Perfect, Lorraine. That was the best word you could have used, the reciprocal. We are going to multiply by 13/12. The reason we multiply by 13/12 is because now I've got a 13 on top and bottom. I've got a 12 on top and bottom, and all that's left is the x. Over here, I'm going to multiply by 13/12 also. Whatever I multiply by on the right, I have to multiply by on the left. As I look over here on the left-hand side, I can see now I've got a 13 on the bottom and a 13 on the top. So I can cancel those. And what I'm left with over here on the left-hand side is just negative 84 over 12, and that's equal to x. That could be my answer, but I'm going to go ahead and divide it. You know, it's an expected value type question, and negative 84 over 12, that doesn't mean a whole lot to me. I'll divide that and get negative 7. And what I've just found out is how much must they lose in order to make this game fair? When they lose, they need to lose $7. So if they're going to win $84 by picking the ace, in order for this game to be fair, they need to lose $7 when they pick any other card. That's the most challenging question we'll see today. We saw a whole bunch of expected value questions. This one, where we have to find out how much they would lose, is because of the algebra involved, is a little bit harder than that. We've got enough time left. I'm going to go ahead and have you try one of these with a poll, and then we'll work through it again. I kind of want you to see a second one of these. So that's part of the reason. I want to give you a chance, and I want to work through a second one. So let's go ahead and look at another one of these that I'll set up a poll for. A single die is rolled. If the result is a 6, the player wins $65. In order for this game to be fair, when the player loses, how much must they lose? So our structure is the same as the last one. In order for this game to be fair, well, in order for a game to be fair, I know the expected value has to equal 0. So I'm going to know all of my results except for one. I'm going to know my probabilities, and I'll know the expected value has to equal 0. I'll set up an equation, I'll solve it, and I'll know how much must they lose. So I'm going to set up a poll for this, but I am going to give you a little bit of a kickstart. A player could win 65 or lose, I don't know how much. They're rolling a single die. If they get a 6, they win. So the probability of winning is 1/6. The probability of losing is 5/6. With that in mind, how much must they lose? I'll set up a poll for this. I'll only give you a couple minutes because we don't have a ton of time left, but I want you to have a chance to try it if you feel comfortable taking a run at it. One thing I will say is you're going to see all positive numbers there in the answers. The reason for that, the x that you solve for is going to be negative, but it's the way the question's phrased. How much must they lose? Well, you wouldn't say they lose negative number. You would just say they lose that number. So that's why the answers are written as positives here. But when you solve this equation, you can expect a negative number for x because it's indicating a loss, not a win. And like I said, I do want you to see this worked out again. So I'll give you less time than I typically would. Maybe another minute, and then we'll do it together. And so when I cut this one off, I apologize for doing it fast. If you're not done yet, you can keep working on it and get to the end and then see how yours lines up. And I don't have to cut us off, right at 10:50, but I don't want to, I don't want to drag it out too far. All right. So I'm going to go ahead and publish the poll so we can see where we are. But if you're still working on it, you keep going and then look at yours and look at ours as we work through it together. Oh, hey, not bad. That's pretty good, given that we kind of went pretty quickly through that. That's a good result there. All right. So as we set this up, what we see that we have here is we have our expected value, which we know in this particular case has to be 0, is equal to 1/6 times plus 65 plus 5/6 times x. In order to solve this equation, the first thing we're going to do is go ahead and multiply here and have 65 over 6. And then in order to get rid of 65 over 6, we're going to subtract that from both sides. What that does is it gives us negative 65 over 6 on the left, and that's going to equal 5/6 times x on the right, because these have canceled. Now I'm trying to get that x by itself. I need 5/6 to go away, so I'm going to multiply by 6/5 on the right and multiply by 6/5 on the left. These cancel, leaving me just the x, which is what I was trying to do. On this side, the 6's cancel, and I have negative 65 over 5 is equal to x. And when we divide that, we get negative 13 is x. And so the question of how much must they lose? They have to lose $13 when they lose. In order for a game to be fair, the expected value has to be 0. That fair means the house doesn't have an advantage and the player doesn't have an advantage. The expected value is 0.